Welcome everyone. Today we are going to learn something about roots of equation. As you can see, it's a very familiar topic to you just because you have learned this thing throughout your SSA life, also HSA life as well, and now we are here to reveal something new and new dimensions on this particular topic just because as it is similar to you, so analytical solution you might be very familiar with, but in most cases, as we are saying from the very beginning of this course, that in real life scenario most of the problem arising in front of you will not be able to solve those analytically. Rather, you will have to go for the numerical solutions for most of the equations. So that's why roots of equation will be trying to reveal some new dimensions and not necessarily just analytical solution. If not possible, then we will go for the numerical solution, just not for that, but also if we think about the computer programming, we'll have to teach our computer as well how to perform and how to solve the equation, just because the computer can do nothing but the calculations or repetitive tasks. So we must teach this computer to act accordingly so that it can give us the solutions or roots of equation which it cannot do analytically of its own. So that's why we'll need to learn about the numerical techniques, as well as we'll have to think about how we might teach the computer the iteration or iterative tasks so that the computer can give us the answer. So let's start this topic. What is roots, or what are roots? If I ask you, years ago you learned about this thing, x equals to minus b plus minus root over b square minus 4ac divided by twice a to solve ax square plus bx plus c equals to 0. This is very common equation which you have learned so far, yet there are many more functions for which roots cannot be determined so easily, just because of the complex nature of the equation. The parameters to be determined may be implicit, and in those cases you will not be able to solve those analytically as well. So for example, if I review the problem what we have discussed in the very first class, if you see about this example, this equation, this is an tan hyperbolic containing equation. As you can see from this equation, you cannot determine the value of m from this equation in analytical approach. So that's why this is very complex to determine, or it might be impossible. So that's why in these cases what we do, how to determine the value of m. If I ask you what will be the value of m when the value of velocity is 36, in those cases we'll have to determine the value of m. So the equation, when an equation will become in such a structure, it will be following that all other things are represented using numbers. Only the unknown is one variable, then that will be called the value of that variable for which the equation will be satisfied. That is called the roots of equation, as you all know. Or we can say, if we focus on our script, if I say this is y equals to function of x, we can say if it is like something x cubed minus twice x plus 3. So if it is the function, we say that when the function of x will be equals to 0 for the value of x, and that x will be called the root of that equation, this equation. And as we all know that root of equation might be multiple rather than a single root. It is possible in most other cases, and usually we determine the number of roots from any polynomial. We focus on the higher order. The highest order indicates the number of roots. As we can see here for this particular equation, the power of x, highest maximum power is 3, it indicates that there will be 3 roots of this particular equation, no matter whether all the roots are real or imaginary, it doesn't matter. But the roots will be, number of 3 roots will be getting for this particular equation. That is the fact, first of all. And in case of imaginary roots, as you all know that imaginary roots, we obtain these imaginary roots in pairs. That means whenever you will be obtaining imaginary roots, the number of total imaginary roots will be an even number. So either there will be 2 imaginary roots, or there might be 4 imaginary roots. So this is the fact how we will be dealing the equations. So 3 roots, that indicates at least one root will be real. At least one root will be real, beyond doubt. I can say that at least one root will be real for this particular equation, and there is possibility that 2 imaginary roots might be there. That will be only getting when we'll be solving this. Other than that, we cannot say whether it will be imaginary roots or not. We cannot say. However, this is the main thing, that whenever all other values are known except one variable within the equation, and the total equation becomes equals to 0, then this is called the value for which the variable, the satisfying variable, the equation is satisfied, so that the total equation is equalized in both sides. That will be called the roots of equation. And for this particular roots of equation solving, we usually make one approach, that we take all the variables and all the numbers in one side and we make this equals to 0. So we determine for which value of x or the variable the total equation will be satisfying, or the side, the left hand side, say for example, will become 0 just because the right hand side is also equals to 0. So that is our main concern when we are trying to calculate the roots of any equation. So let's move to the slide again. So how to solve this root? Before that, I will be I'll be going back to the script again, that what does the root indicates in actual scenario. If I draw a function within a graph, as you can see here, say this is a graph, this is a straight line. Say for example, I am drawing a straight line here. There will be a straight line, so the equation will be like y equals to mx plus c. So it will have one root, as you all know that the highest order of x is 1 here. That's why there will be one root. And what does this root indicate? If this is y-axis and if it is x-axis, the root indicates that for which value of x, y will become 0. This function of y, a function of x or y, will become 0 for the value of x that will be called the root of this particular equation, or root of this equation. Mx plus c equals to 0. The root of this equation will be the value of x for which this will satisfy. And if we focus on this graph, I am just focusing on this particular point. This is the root of x, if you can understand. Root of the equation, the equation's root will be this one, that is the value of x. There is fxr, and for this value of xr, the equation will become 0, and that's why this will be called the root of the equation. So now, if it is a function, I'm now drawing a curve-shaped graph here, a function of curve shape I'm drawing here. So this is a function. This is a function of x equals to y, and we don't know the solution or the root of this equation, for which this will be the solution for which the function will become 0, this one, and this is our expectation. Now how to solve this, that is our main question. Say for example, first of all, you don't know the value for which it will become 0. The one thing we know that we can go for the analytical solution, our ordinary analytical solution, ax square plus bx plus c. It will be like this function will be like this one, obviously, just because it's a shape of parabola, as you can see from the graph. It will be like this one, so it might be a parabola. So that's why for this equation we can write this is 0. So analytically we can solve for this, where ABC is known, but we only this one will be x. So ABC is known, only we need to determine the x value for which the equation will become 0, 0 in both sides. So that will be the root of this equation, or roots of this equation. There might be multiple roots in this equation. So how to solve this instead of using the analytical solution? That is our main concern in this particular topic today. So now we'll be moving to the slide again. Now we come to the point. What are the numerical solution techniques? There are major two categories of solution methods for the roots of equations. You might have learned or heard these things about these things in your HSC life. For example, I can say I can remember about bisection method or Newton-Raphson method whenever we have conducted our lab mathematical laboratory in HSC level in Notre Dame College. So in those classes we used to draw in graph these particular methods we tried to follow, and we try to solve the roots of equation. But in this course I will be going in details about the calculation, about the philosophical background behind all these solution methods. We'll be learning about this. So the major two categories are bracketing methods and open methods. The main difference is in bracketing methods we'll be trying to cordon that particular root. Will be try to assume that within these two particular values, that is, we'll be assuming two values here. In case of bracketing methods, we'll be trying to fix two points within which the root will be lying. That is the main theme of bracketing method. Whereas in open methods we need only one point to predict to start with, and then we'll be going through and moving close to the original roots in open methods. So the main difference is in bracketing methods we need at least 2 points, and for open methods we can use one points, or we don't need to cordon the root, the predicted assumed root, wherever the root is lying within this range. We don't need to predict from the very first iteration of our mathematical approach or these methods. So these are the main difference. This is the main difference between the bracketing methods and open methods, and the examples are given here. As you can see, bisection or half interval search, and another method is a method of false position or Regula Falsi. And in open methods we can give example about Secant method. I can give example about Newton-Raphson, or there are iteration methods, and many more methods are available there in numerical techniques. So instead of using our traditional analytical approach as we have learned so far, we will be going for other methods, other numerical techniques or solutions for solving all the roots of equations. So equation might be in different form. Maybe it might be in algebraic equation, x squared plus bx plus c, or it might be in transcendental form as well, as you can see from there, 1 plus cos x minus 5x equals to 0. So this all structures can be available, as you can see from here. So whatever it is, now we'll be giving example about, we'll be starting from the bracketing methods. I will be trying to give at least one method examples from each of this, and each of the two major categories. So I'll be trying in my lecture I have prepared this so that I can cover one bracketing method and one open method, and we'll be also try to learn something about this regular Falsi method as well. If you are very expert in learning these things or performing these tasks in your hand calculation, you will be also able to create computer program based on this solution techniques to solve all the equations using numerical methods. So numerical solutions methods in bisection method will be starting here. And before that, I will be trying to say something about bracketing methods again. This is called the incremental search, and also called incremental search just because I will be increasing our search so that we can go as close to the solution as possible. Brackets are formed by finding two guesses, xl and xu. L means lower limit and u means upper limit. Where the sign of the function changes, that is where the fxl and fxu less than 0. So I am just making you understand about this fact. Let's go to the script so that you can understand this easily. And let's give example of this one. Let's give example of this one. Okay, I'm again drawing the graph, and now I'm drawing a function like this one, say for example, or very curve shaped. Not like that. Okay, this one might be the example. So this will be the root, our desired root, which we don't know from our initial guess, but we know we are trying to take one upper and one lower limit. One upper limit and lower limit here. So upper limit means that this point is xu, and this point, the lower limit, will be xl. So this xl and this will be xu, upper limit and lower limit of x, initial guess. So the value, this is function of x. So we will be assuming that if the sign changes, that is if fxu having one sign, that is in this case this is positive, and fxl, this point, is in negative portion, so xl is in different portion. So if our case says if it is the multiplication of these two, if it is less than 0, that is the signs of these two are different from each other, that means the sign changes only when it crosses, the function crosses the 0 point in the function, either from this side or that side, whatever you say. Whenever this function, it is positive, it converts into negative, that means it obviously crosses the 0 point in between these 2 points. So that's why we say this is bracketing method, and this is the main concept of bracketing method, that we will be cordoning our predicted root from two sides so that we can confirm that, make a confirmation about this thing, that the root will be lying in between these 2 points, and these two will be our initial guess, and we'll be trying to approach close to this particular solution, this true root, and that will be our task in different methods. The main concept of bracketing method is this one, to cordon this from 2 points, the 2 points for which the function will give 2 different values, from which we can say that yes, within these 2 points the roots will be lying, our desired roots which we are talking about. So that is the thing what we have mentioned in our this slide. In this particular figure I have also shown this. The incremental search method tests the value of the function at evenly spaced interval. Okay, so in evenly spaced intervals we'll be searching for the value of the function. So the methods, if we go in further division, that the bracketing methods, we are dealing with bisection method now. What is bisection method? Bisection method, the main thing, this will be bracketing method. Obviously, as you can see, there is a lower limit, as you can see also there is an upper limit. Within these two the root will be lying, we know, but in which point the root will be lying, that is our main concern. So we need some iterative techniques so that we can get close to the original solution. In bisection method, it says whenever you have defined our upper and lower limits, next task of you will be to get the middle values or the average value of these two, which means I will be predicting the middle value as XR. As you can see from there, this XR is the middlemost point, the average point. So if we sum up XL plus XU divided by 2, we'll be getting this XR, and this XR is our initial guess of the root, although the original root, as you can see, is lying over there. As you can see, original root is close to 150, but our first initial prediction says this is XR. So we need to get close to the original solution. So what we do, the next, our this XR will be calculating the value of fx, that is the function we will be calculating. So if we see that it is not equals to 0, obviously it will not equals to 0 in this case, so it will be either positive or negative value. So if our lower limit, if it says that our lower limit is indicating the negative value and our upper limit indicating the positive value, in this case it may be of different form as well. The lower limit might be negative and upper limit might be lower limit might be positive and upper limit might be negative as well. It doesn't matter. Lower limit means the value of x is least, and upper limit means the value of x is highest. Within this the root will be lying. It doesn't matter, the lower limit x for this one, function of x might be positive, and for fxu, upper limit xu for that function of x might be negative. It doesn't matter. Don't think about that xl, lower limit, will be always giving you fxl equals to negative value. Not necessary, but whatever the value are, if these two will be changing signs. If fxl is negative, fxu will be positive, or if fxl is positive, fxu will be negative. That is the main thing. Lower doesn't mean that function of xl will be lower, that is negative. Xl means lower, xl means the value of x is least. Say if it is 50 and if it is 200, then it indicates that xl is least is 50. Not necessarily fxl will be negative, that's why this is lower limit. Just remember this thing, otherwise you might make mistake in your exam. So please try to understand this thing. And after that, what is our next step for this? If we understand this xr, you will be calculating fxr. If we get fxr value is negative, for example, then you you will be forget about this Excel. We'll be replacing the new Excel as this one, XR. This XR will be become new Excel. So first of all, what we'll be doing, say we know that this is negative, we'll be writing in short note that this is positive and this is negative. XR, this XR, if it is negative, it will be replacing this negative value. So this will be our new XL. XU will remain constant in this case. So again we'll be determining the middlemost value, and this value again is not equals to the original root, or neither it is very close to the root, so that our criteria satisfies. So now we'll be again trying to calculate fxr in this case, and this time it will be positive, I hope. So that's why, as it was positive and this is also positive fxr, so it will be replacing this value. So this one will be cancelled and this will remain constant for the next step. So in third iteration, as you can see, this one will remain constant and this xr is replaced by xu, and the new middlemost value is xr. So as much as we will be going through this, the next steps, fourth iteration, fifth iteration, we will be getting close to the roots, as you can see from this particular approach. So that's why this is the bisection method. This is our main philosophy for obtaining the roots or getting close to the original roots using this bisection method. Why we call this bisection method? Just because we are bisecting these 2 points and we are getting the middle points each time in this particular example. And that's how we will be going for the final roots. So whenever the criteria for our method will be satisfied, we'll stop there and we'll say that okay, this is our expected value. Now, bracketing methods in bisection, the absolute error of the bisection method is solely dependent on the absolute error at the start of the process. That is, from which you will be starting, you can determine the absolute error for how many numbers will be required. You can easily calculate from there that how many iteration or steps will be required for calculating or obtaining a particular value of absolute error. That you can easily calculate using this particular equation, which I will be, and from this you can reform this into this one, so which we can I will be explaining you whenever I will be solving the problem. I will be making you understand about this. Just for the time being, you think this one, this EAN, that means the absolute error at nth step, which we'll be getting, is equals to del x naught. That is, if we start from the very first iteration, then the del x means the difference between the lower limit and upper limit, xl and xu, that is del x naught, and divided by 2 to the power n. This n is the nth step, for which we will be getting this absolute value. So we can easily determine this one indirectly, and very first of the starting of the problem. We'll be learning it how to determine in practical example now whenever we are solving the problems regarding this. So let's go to the problem regarding this. I'm going to solve a problem using bisection method. As you can see, the question says, determine the drag coefficient C needed for a parachutist of mass m equals to 68.1 kg to have a velocity of 40 meter per second after free falling for time t equals to 10 seconds. Acceleration due to gravity is 9.8 meter per second square. Start with initial gaze of 12 and 16, that is, the initial gaze xl and xu are given there. Equation of velocity of parachute is this one is given. So now we'll be trying to reform this equation, and will be all the values are given except this c value and this c, for which we'll be trying to solve the roots of equation, and the stopping criteria es is given. And now you might ask me the question that whether the stopping criteria indicates the stopping criteria with respect to which error, whether it is epsilon A or whether it is epsilon T. That is, whether it is a true error or approximate error, which will be determining here. So now my answer will be like, if you can determine the true error, obviously you can go for the true error in this case. But if you don't be able to solve this using the analytical solution, or you cannot obtain the true root of the equation, then obviously you will have to go for the approximate error. And yes, in this case you will not be able to determine the solution analytically. That's why you'll have to go for the absolute error in each step, and for each step you will be comparing your absolute error epsilon A percent relative epsilon absolute error with this epsilon S stopping criteria, whether your error is less than this one or not. Whenever the value epsilon A will be less than this epsilon S, then you will say that okay, the value obtained for this step, that will be our answer. We don't have to move further, and this is the root we are expecting. So let's not waste time and solve this problem. I am just copying this one in our script so that we can solve our problem easily. Okay. This is the problem. Now we'll have to solve this using bisection method. Okay. To start this problem, before we start this, I need to reform this particular equation like gm by c 1 minus e to the power minus c by m t minus v equals to 0. So that is our perfect equation type. Now I am putting the values 9.8, the value of m 68.1, the value of c will be c 1 minus e to the power minus c by m, that is 68.1, multiplied by the time, that is the time says 10 seconds, so this will be 10, minus v, the velocity is also given there, a velocity of 40 meters per second, so minus 40 equals to 0. So everything in this portion left hand side, and it equals to 0, and this is, we can say, function of c, which we need to make this equals to 0 for which value of c, that is our main concern for this particular math. So as you can see, the two limits are given there, 12 and 16, so we can easily say this is instead of xl xu, we can say this is cl equals to 12 and c upper limit equals to 16, and so calculate these two values. Function of cl will be equals to, this is the function of c as we have derived here. So the value of fcl will become 14.7802, and for cu equals to 16, if I say the value of cu will become, let's calculate this thing, and this will become minus 2.2688. So this means CL is giving you a positive sign and this is giving you a negative sign, and the limit lower indicates this is 12, the least value, and 16 means the highest value. And as we see from here that there are two signs which are different from each other, so we can say yes, within these two values the original root of this equation will be lying. So this FCL multiplied by FCU is less than 0. That means signs of these two are different, and that's why it will be less than 0. So we can say the root is lying in between this 12 and 16. So we'll be starting here. We'll be drawing a box. A table will be drawing here. In this portion I am writing iteration. I'm writing iteration here, and the next value says this is the lower limit, and then we'll be going for the upper limit, and then we'll be going for the CR for the term that is obtained, the middlemost value of these two, that is CR for each step, and finally you will be calculating ER, epsilon A in percentage here. So our stopping criteria was epsilon S equals to 0.5%, as you can see from the question, stopping criteria. So whenever the value of epsilon A will become less than 0.5%, then we'll be stopping, and that particular CR for that particular step will be our answer. So now to start with, the first iteration says we'll be starting with x equals to 12, CL equals to 12, and CU equals to 16, and this indicates negative. In short note you can write, and this positive. In our case it might be, this SL might be positive or this XU might be negative, it doesn't matter, but you will have to remember or write a short note over there, just because the CR, for this CR, the function of CR, if it is positive it will be replacing the positive value as it is positive. If it were this one were the positive value, if it becomes positive, this value in the next step will be replacing this one in that case. So in our case this is negative and this is positive, and based on these two we'll be making approach with. And the CR for bisection method, CR is nothing but equals to CL plus CU divided by 2 in each step. So for this step we can easily calculate this as 16 plus 12 divided by 2, that is 14. And in first case, as it is absolute error, so we cannot get any values for this one. Now in the next iteration, the CR, now we'll be trying to get the values of FCR, that is F14 in the equation. In this equation we'll be putting the value of C as 14. So we'll be just needing the sign of the FCR, whether it is positive or whether it is negative. That is our main concern here. So possibly for 14 we'll be getting the value as negative for 14, so that will be replacing this value, and this will remain the same. For the next step, this is CL and this is CU. That's why the CR will be calculated as 15 in the next step. So now we can also calculate the epsilon A as well. Epsilon A from our constant, it is the previous value. As we know, we will be calculating the absolute value in our case. That will be better for us, as the stopping criteria is 0.5%. That means it is absolute value, obviously, no doubt about this. Not the negative or positive will be matter here. So that's why epsilon A is the value, the previous approximation minus the present. As you all know, this is previous and present approximation will be there divided by the present approximation multiplied by 100%. That is the epsilon A, and will be determining it in absolute value. So the value, if we calculate from here, that will be previous approximation minus present approximation divided by present approximation multiplied by 100. It will give us 6.667%. So that is not the case where this epsilon A becomes less than 0.5%. So we'll have to go for the next step. Now we'll be again determining FCR. So we can use another column might be there, which I have forgot to show. You will be showing in your case. So I'm just removing these things for the time being. So there will be another column here which indicates FCR sign. So in this case it was negative, and epsilon A percentage, first one there was no approximate error in the first step. In the second step we have found this as 6.67%. So in the next step 15, so FCR sign will be calculating to see whether it is positive or negative. In this case it becomes positive sign, FCR. So that's why it will be replacing in the next iteration, as it is third iteration as we are seeing. So it will be replacing the value of 16 as it is positive. So it will be 14 and 15, and this will be 14.5. Average of two values. In this case, now we try to calculate the value of epsilon A. In the similar manner, we'll be getting, this is the previous value, this is the present value. So using these two, we'll be getting the value as 3.448%. And now we'll be trying to determine FCR, and this will be negative in our case. So the next step it will be replacing this one. So 14.5, 15, and this will be 14.75 in the next step. And for this, the approximate error, percent relative approximate error is 1.695%, and which is again not less than our desired value 0.5%. That's why you will have to go for the next step as well. Now calculate the sign FCR for this 14.75, and this will be again negative, so it will be replacing the negative value here. So 14.75 and 15. So now we can understand the root will be lying in between these 2 points. As you can see, within these two the original root lies, and the average of these two is 14.875, as you can see. And absolute error, if we calculate from here, it will be 8403%, and which is again not less than 0.5%. That's why we'll have to move further for the sixth step. So FCR value now will be calculating. This value gives you a positive result now. So this will be in the sixth step. It will be replacing this upper limit, that is 14.875, and in this case our result says this will become 14.8125, and now if we calculate the absolute error, in this case this will give you a value of 0.4219%, and this is less than 0.5%, our stopping criteria. So we don't need to calculate the sign here, and just because we can stick to this result. This is our desired result for our stopping criteria. So this will be the answer for our particular case. So we can say the value of C will be 14.8125. This is the desired answer. So you can add the unit here as well, the unit what you can get obtained from this equation. You can calculate the unit of this particular C coefficient, which you can also use with this result. However, so that now this is the method of bisection, a bracketing method. So from this example you can see we need very large number of iteration to converge. The absolute error is decreasing very slowly, as you can see here. So this is a problem, just because when this will create problem whenever you have started with an example where this might be the case. This is the function. You have two initial gauzes. One is very close to the root, but another one is not. So this is very far from the root, and this is very close to root. In that case, in each step you are getting values like this one, this one, this one. Slowly it is moving towards the solution. Whereas if it were in the middle portion, the two gauzes, this one and this one, say for example, that might be very easier for you, just because in the first case you will be getting very close to the solution, average, making average of these two. So the problem of this bisection method is, as we are always taking the average values, so depending upon whether the upper value and lower value, if it is not equidistant from the original root, then it will take large number of iterations to converge and get to the original solution. So one improvement can be done for this problem, that is the next method which we'll be discussing about, that is the regular Falsi method. So let's move to the slide again to discuss about this. The false position of the regular Falsi method indicates that we will be not going for the average value here like bisection method does, just because it that will take you a large number of iteration to converge and get to the original solution. Instead of taking the average value in parallel to x-axis, if you can remember, in our case we had evaluated the average value in assuming this straight line. This is xu and xl. We have evaluated the middle point using this one in case of bisection method. So forget about this thing. That's why it might give you a point in this point in the initial gaze, which might be a problematic thing which will arise in the bracketing method or the bisection method, which we have discussed in the previous problem. So what we can do, an improvement, we can join fxl and fxu by a straight line, not taking the bisection method in parallel to x-axis. Rather, we just connect this fxu, this point, and this fxl point. These 2 points will be joining with a straight line, and this straight line, the point where this will be intersecting the x-axis, that will be our xr, that is the initial gaze of the the root, although this is the original root. well, whatever the x-axis intersection point of these two connecting point, how we can determine this XR? If it is XR for assuming two equivalent or two triangles in these two portion, as you can see here. So we can assume, we can take this similar triangle concept. If we take we can write down this two equation, fxl this one, this portion, and fxu this portion, and ratio of this one, this portion is xr minus xl, and this is xr minus xu. So from these two we can derive another equation from which xr can be determined using this particular equation what we have derived here. And this will be our new guess. Instead of xl plus xu by 2, what we have done in the bisection method, in this case we will be calculating xr using this particular equation. And the fact that the replacement of curve by a straight line gives a false position, that is, this is a curve function originally, but we are connecting this as a straight line, as you can see. So replacement of the curve by a straight line gives a false position. This xr of the root is the original of the name method of false position. That's why we call this as a false position method, or in Latin it calls Regula Falsi. So it is also called the linear interpolation method, as we are interpolating it linearly like this one. This is a linear interpolation equation. If you can remember from our the last class, if you can recall in your mind. So this is nothing but the linear interpolation method also, you can say. So using this method, there is a task for you to conduct the same thing and testify whether we are getting the approximate value in a shorter step using less amount of steps or not in using this false position method. So that is our next task. I will be just touching this thing, I will not be completing this thing. You will be completing this thing. I will be showing maybe one or two things or one or two steps, and after that you will have to make approach about this. So in case of a regular falsi method or false position method, in our case I will be saying that first one xl, okay, I write xl instead of cl, that will be more comprehensive to me. So if it is xl equals to 12 and xu equals to 16, and we know that fxl equals to fxu, these two was positive and negative one. So 6.0699 0688 maybe the value was, if I can remember, 60 if it is, okay, I can't remember the original value. Let's calculate this thing again. 9.8 multiplied by 68.1 divided by 12 multiplied by 1 minus epsilon minus 1210 divided by 68.1 minus 40. Okay. Okay, for 12, if we say, if it is 12 in our case, it will be I had made a mistake while describing this thing here. It will not be 14.78, although it will not make impact on our calculation, just because this is only the sign what we are dealing about. It will be positive signs. It will be 0.669. Okay. 0669 in our case. So this one, and so nothing will be changed here. So 0669, and this one, as we have calculated, 2.2688. So from these two values, using regular Falsi method, if we use the regular Falsi method to calculate XR is equals to we take the values. This is the formula for us. So XU, that is nothing but the value 16 will be there, 16 minus FXU, that is minus 2.2688, and XL minus XU, that is 12 minus 16 divided by FXL, that is 6.0669 minus FXU, that will be 2.2688, I think. So it will become like 14.9113. So this is our initial case. So think about this thing. XR, the first iteration, this is the first iteration, it is giving you a value like, first iteration is giving you a value 14.9113. Whereas in bisection method, the first iteration you have obtained 14, then 15, then 14.5. We are close to 14.8125 after 6 iteration, if you can remember. Whereas in the first case, it solely says XR equals to the initial this first step gives you the value of 14.9113, which is very close to the solution. However, this is the first iteration, that's why you cannot calculate any epsilon A here. So you will be again creating chart like what we have done in the previous case, iteration, then XL, then XU, then XR, then sign will be obviously required here. That is, this is the sign of FXL. This is sign of FXU. Don't be confused about this. Not the sign of XL or XU. Okay. Then sign of FXR and epsilon A percentage. So the iteration 1, 12, 16, it is giving you 14.9113. Now no error we can determine here. So for 14.9113, whether this is positive or negative. Now the next question comes. Now I will be calculating the value of FXL and FX. The second iteration, I will be watching whether I'll have to replace it with positive one or negative one. So from our calculation, we'll be getting this value is positive. So it will be replacing this one, 14.9113, and this 12 in the second iteration. Now the XR, if you calculate using this formula, now you have XL, if you have XU, you need to also calculate in regular Falsi method one additional column you will be needing, which I forgot to write here. Another additional column, no, not additional one column, rather you will be needing, you see here, FXL, FXU, two things are required here. So two additional columns will be there in between these two. So better we take these things as in this side, and before that we need two columns, as I have said, the value of fxl and fxu are required here, so that we can use this in this equation. So fxl, fxu we have calculated here, this one and this one, which we have used. So we will be writing these two values here, and fxl will be remaining the same thing, 6.0669 if I'm not wrong, 0669, and the fxu will need to calculate now for this particular case. So this will be, fxu will be minus 0.2543, minus 0.2543. Okay, obviously these two will be of opposite signs. So in our case, what this was actually negative. I was totally wrong in our case. So please correctify this one, that the upper limit, this was our negative value. So although I haven't shown the calculation, that's why I have made mistake here. This was negative and this was positive. So this is the positive thing and this is the negative thing, if you can remember. This is the negative thing. So that's why the value, first one, the 14, this 14 value was replacing this one, just because this will give you a positive value, and this is replacing this one just because it will give negative value. This is positive, and this will give you negative value. So please correct this thing. Other than that, I don't think the calculation is wrong, just the sign was the problematic in our case. I think you will be able to understand this thing, just because I have made a mistake here. This was positive and this was negative in our case. This is negative, this is positive actually, and this is negative. So this will be positive and this is negative in our case. In all cases this will be positive, this will be negative in regular falsi, and it is replacing just because it will give you a negative value. That's why it is replacing this one. So if you have confusion, you can again calculate this using the equation what we have obtained, 14.913113. Using that value you can calculate the value 14.9113, and this will give you obviously negative value. Yes, the value of this one is negative, and that's why this is replacing this one. As you can see, again, this is the value, this is negative, this xu, this is this one. So for this fxr is negative, and this negative means this value, just because it has replaced this 16 here in this state. So however, now using this xu, xl, fxu, fxl, you will be again calculating fxr for this particular step, and if we use all these values to calculate this one, we'll be getting, in our step, we'll be getting 14.7942, 14.7942. And if you calculate epsilon a using this one and this one, you will be getting the epsilon a is equals to 0.79%. Can you imagine 14.7942 in 2 steps? In 6 steps we have obtained 14.48125. So this regular falsi, you can say, as an improvement of the bisection method we have learned before. So this is a technique how you can improve your assumption, and you can minimize your time, just because the computer will also need time for each of the iterations. So if you use a regular falsi method For computer, in most cases it will take least amount of time, or at least you can say less amount of time with respect to the bracketing, the bisection method what we have discussed before. So I think you don't have any confusion regarding this sign anymore. What I have made mistake I have clarified here now, so I think you will not have to worry about it further. Now I will be getting to the next, going to the next slide. Let's move back to the slide. So this was the problem, and now we'll be talking about the problems with bracketing methods. What are the problems if we use bracketing methods? Some problems, root finding methods may fail in this case. If you can see here, the explanation is given. If you think that there is same sign but no roots in between these two, same signs, you cannot find any roots. Say for example, this is a graph, this is our curve. This curve has no real solution. Our technique gives us real solutions or real roots. It doesn't have any real root, as you can see, just because it never intersects or crosses x. So it will be going to these two directions, like as you can see from this. So it will have imaginary roots, two imaginary roots will be getting. But in this case, what will be the initial guess? You can take guesses or guesses after guesses, but you will be always getting xl, function of xl and fxu, always getting positive values. So you cannot get any sign change over there. And if you don't know the shape of this graph, and the computer will not know about this, so if you impose the bracketing method over this one, and this will go for infinite time, but it will not be able to give you any solution. So it will create problems. So the bracketing methods, one limitation of bracketing method is this one. So now if we move back to the slide, the second one says same sign, two roots. This is another hazard. If you see here in the second figure, that you have same signs, but in between these two you have two roots. So one might say, why we are not getting the values where the sign changes? That is, you might ask me that it is changing sign in this portion. So why I am not taking this value, rather I am taking this one? Well, I am showing you in elaborated view. That might be like it is 4 and this might be 4.05. So you cannot guess. Most of the time you will not be able to guess. You might ignore this. Okay, for 4 it is positive. Okay, for 5 it is positive, or at least you might have think about 4.5 or even 4.1. So for 4 positive, for 4.1 positive values throughout. So you don't know that within these 2 points one or two roots lie within this 2 point. So you are just ignoring this, but you cannot determine this one. So the bracketing methods, as we must fix sign changing within the root in two sides of roots. So in the cases where we are missing this, that case you might face it very complex for you to solve. So this is the second one, the second problem. Now come to the third problem, which arises from the bracketing methods, and this is the different find three roots. even if, that is, even if you have got two different signs, even if you have got two different signs, say for example this one, two different signs you have got, you might be very delighted. Yes, I have obtained two different signs, xl and xu, and fxu is negative, for example here, and fxl, it gives you a positive value. So you might be very delighted that, oh, I have got two different signs. But it is possible that within these 2 points, not only one, there might be 3 roots lying. This is also possible. And why this happened? Just because this might be 4, you have thought, and this is 4.05 maybe, for example, but it was, and these 2 points, these are 0.0025, and this is 0.0015. This is possible, but you cannot imagine these things here while taking initial gaze. So you might have obtained even 4 and 4.05. Okay, sign changes. So let's take, this is xl and this is xu. But even then, within these two, there might be 3 roots available, and in that case, your total assumption or the philosophy behind this technique, bracketing method, will be collapsed, and you will not be able to find the original solution, and that will create complexities. So this will not work. So for mitigating the problems with bracketing methods, that's why we sometimes recommend these open methods, and from which we will be discussing about the Newton-Raphson method here, where only one point is enough for you to predict the value or the root of the equation, where you don't have to cordon the true root, rather you can start from any point, any open point, that will be, you will be getting the values, the original roots, I hope. So open methods require 1 or sometimes 2 starting values, but which do not necessarily bracket a root. The first thing here, that is, it might require 1 or might require 2 sometimes, but the thing is that it will not require necessarily it should bracket a root. That is a thing here. So it may diverge or it may converge. It is a problem here, that is, whether it will diverge the origin from the original root, or it will converge towards original root. That is a concern here. If they converge, then the positive thing is that they converge at a faster rate. So very fast rate it will converge. Example of Newton-Raphson, which will give you a clear overview regarding this, I hope. So let's talk about Newton-Raphson method. One example of Newton-Raphson method, the philosophical background is shown here. Based on forming the tangent line to the fx curve at some gauge x, then following the tangent line to where it crosses the x-axis. So open point, so any point you can take. So let's, you have assume the first point as xi. This is your initial guess, any point. So any point, for that you are calculating slope at that point. So fxi you will be getting, and also you will be getting the slope at point x. So Newton-Raphson method says where this point slope will be intersecting the x-axis, that will be your next case. So think about it, you will be getting close to the original root. This is the original root. The initial gaze is xi. For that you can calculate fxi, and for that you can calculate the slope, differentiating this equation of fxi, and then you can understand where it will be intersecting the x-axis. That is, this will become 0, in which point, that is your main concern, and that point is our next case. This is the slope, and this slope is intersecting this point as this is xi plus 1, and this is our next case. And from there you will be again taking for this point, this is fxi plus 1, and the slope again you will be getting more close to the original solution. So that's how you will be approaching towards the original root, and very convergence. Once it converges, then you will find it the first rate of convergence, which will swiftly it will give you or move you towards the original root, as you can see from this particular figure. And how to calculate the slope? This is f prime xi. This is the formula of slope. We know the slope is nothing but y minus y, y2 minus y1, x2 minus x1. This is the formula what we have used here. If it is x1 and if it is x2, this is y2 and this is y1. So using these values, x2, this is x2, so from so this is not x2, sorry, I have made a mistake. This is x2, just because I am taking the slope like this slope, whenever I am dealing with this slope, that means we have a point, this is the point, this is one point, and this is one point for this particular slope, this straight line. So this is x1 y1, so this is x1, this portion, and this is y1, and this is x2, this portion, this is x2, and y2 in this case will be 0, just because this is crossing the x-axis. So that's why I am saying this is fxi, so this is y1. So if I say this is y1 minus y2, x1 minus x2, all the same thing. So y1 is this one, this is fxi, and y2 is 0, as you can see here, 0. Xi is this one, xi, x1, and x2 is this one, x2. This is xi plus 1, the next case. So our main task is to calculate this next case, xi plus 1. So I have rearranged this thing, this equation. From rearranging, we will be getting this particular equation. So this will be our prediction, the predicted equation for the next iteration, the what will be the value of x, and this x will be getting close to the original solution. Once we know this first value xi, we can easily get xi plus 1, and one by one gradually we will be getting close to the original solution, we hope. So this is the main philosophy behind Newton-Raphson method, using which quadratic convergence, I have discussed about this, and this is the ETI plus 1, that is, you can calculate the next assumption or any of the later value, true error value from any initial value. If you start from, you can calculate the error of the next, any error of the previous one, you can get to the true error of the next step. You can easily calculate indirectly, which will be approximately equals to this equation. We'll be vindicating this thing while we'll be giving example. We'll be watching there. So this is double derivative, and this is one's derivative. And what is XR? XR is the true root or true solution what we'll be dealing with. So remember this thing. So this will be vindicating this thing, although I might not be asking you to calculate this thing, but still I want to make you acquainted with this particular relationship. That's why I have introduced this equation here. Also, one thing I have forgot to give you an example about, that is the bisection method. This one I have said that I will be giving example of this one while I will be solving the math problem. So I've forgotten to tell about this one. Now I will be describing this. So let's move to the bisection method again. This thing you have to remember. So let's move to the script again. In the bisection method, what we have found, if you can remember the bisection method, in the bisection method, it says that if you have if you know the initial gauge, and we know you need to know the absolute error for any state to calculate. We need to calculate here. The formula says EAN equals to 2 to the power n del x naught. This is the difference of first two fxl, xl and xu. This is the difference between these two in the 0th iteration, if we say, the initial, very initial case. And EA is the absolute value at nth state. So we will be, let's calculate for the 6th state. The 6th iteration says that the absolute error, although we haven't calculated absolute error EA, we have calculated epsilon A, that is percent relative absolute error. So let's calculate the absolute error in this case, not the percent relative absolute error. Rather, we'll be calculating only the absolute error, that is this one minus this one. So the absolute error in our case will be EA equals to 14.875 minus 14.8125, which will be equals to 0.0625. So for which step? So this is for 6th step, and this 6 we'll have to calculate, and we'll check this whether we get this thing or not. So, or the indirectly we'll say whether we get this 6 value or not. So if you can remember our equation rearrangement, as we have shown there, if you can see here, n equals to log 2 x naught del x naught divided by EAD. So this thing will be reusing in our case. So the value here will be n equals to n will be equals to, we can rewrite this in our format, although will not be taking like that, we'll be directly using this. So if you take base of 2 log 2 and del x naught divided by EAD, that is, we have found here this one, and this del x naught is difference between XL and XU. So the absolute value always we are using here in logarithm as well, we need to use absolute value, you know. So log 2, this will be XL12 minus 16, that will be equals to 4. So that will be 4 divided by 0.0625. So using your calculator, the base of log is 2. If you calculate this thing, you will be getting equals to 6. That means n is equals to 6 to obtain this amount of absolute error. So this was the significance of my that slide I have shown. So now you can easily understand about this thing. So now I will be moving to a problem regarding Newton-Raphson method, as I have illustrated, and also I will be vindicating the Newton-Raphson methods, the error which we can predict using the one error, we can predict the next error. We'll be also learning about that thing, but before that we need to solve a problem. So let's see the statement of the problem for a Newton-Raphson method. The Newton-Raphson method, there are some problems as well, what we will be I'm trying to discuss before I go to the problem, just because after finishing the problem I will be finishing our class today as well. So let's discuss about the pitfalls of the Newton-Raphson method. Think First of all, okay, Newton-Raphson method is very well appreciated just because in very short duration or iteration, it will be converging towards the original solution. No doubt about that. Once it converges, but if it doesn't converge, what will happen? See this thing. Say you have taken a function like this one, and you have obtained the initial gaze of your point is this x naught. So what will happen? So you are taking, this is the root, our original root, this one. So first of all, I have used this x1. I will be taking the slope at the point, and it is intersecting x-axis in this point. So this is our new gaze. So from this point of the function, I will be taking again the slope, and this slope is going towards this point, and this is now intersecting this one. I am again going to this function at that point, and again taking slope, and now gradually it is diverging from the original root, as you can see, rather than converging. So it might create problems in such kind of cases, as you can see. In this sort of functions might create problem for Newton-Raphson method. Again, for this case, if you can see here, I'm taking the initial gaze at this point, taking slope. This slope is giving you here x1. This slope is giving you here. Although there is no root over there, it will give you like this one, and this one, and finally it will give you far away from this. Although this was the original root, you might be going diverged or going far away from the original root, and you are just giving effort in the vicinity of this particular portion where there is no original root or real roots lying over there. So that might create problems. See about this particular example where this is a sinusoidal curve, as you can see, or oscillating curve, you can also say. The problem arises here if you start from this initial gaze. This slope will give you there, this slope will give you there. Rather than taking to the original solution, multiple number of original solutions are there, but instead of taking it to the original solution, it may diverge and it may go far away from the original solution. However, anyway, in this particular case, when the slope is almost zero, in a case while converging, once you have went to such point where the slope is actually close to zero, that will take you almost up to infinite value and taking you away from the original root. So it might create again problem in Newton-Raphson method. So if in the exam or question I give you I ask you to mention the pitfalls of Newton-Raphson, you might give this sort of figures, and that will be enough. And if you write 1 or 2 lines in it, that will be enough for you. So however, this is the pitfall we have discussed now about Newton-Raphson method. Now we'll be going to the problem, and that is our last problem and last slide for this class. The problem says that use Newton-Raphson method to estimate the root of fx equals to e to the power minus x and employing an initial gaze of x naught equals to 0. And stopping criteria ES is 10 to the power minus 8%. Can you imagine about this? One thing I need to make correction here, that the stopping criteria you will have to compare it with the true root. I will have to mention here, compare it with true root using calculator. If I don't mention calculator, and if you find that this cannot be solved analytically, then you must go for calculator, even if I don't mention about calculator. And if I give you such kind of problems where analytical solutions are available, then you will have to solve that analytically and obtain the true root and compare it with the obtained approximation values. Okay, now I am trying to solve this. Let's go to the script. I am importing this question for our convenience. I am importing this one. So this is our problem here. Now we'll be solving this. Before we solve, we need to recall in our mind what are the formulas we'll have to use. The derived formula, if you can remember, was this one. Xi plus 1, that is the next assumption, next case, will be equals to the current case minus f of xi divided by f prime, that is the slope at xi. So this is the formula for next case. True root, you will be calculating using calculator. In this case, 5671432904. So as much digit as you can, and think about this stopping criteria 10 to the power minus 8%. So I think the maximum digit we can take we should take in this case, otherwise you cannot make convergence with this stopping criteria. And again, one thing we'll have to compare here, we'll be discussing about it again. This was almost equals to fxr, this is the true root, you can say this is true root here, divided by 2 f prime xr multiplied by eti square. I'll be describing this later on. Anyway, now we'll be starting here our problem. So function of x, in our case, what is the function of x? Function of x is e to the power minus x minus x. So we can write, as we need to determine this one and this one, so we can write xi as xi. So this will be our function of xi, and function prime xi will be equals to minus e to the power minus xi minus 1, first derivative of the function. And we might also need this one later on, so better we calculate this before. So f double prime x will be e to the power minus x. We'll be using this later on. Anyway, so we can simplify. The next case will be equals to xi minus e to the power minus xi minus xi minus e to the power minus xi minus 1. So that will be our next case. So now create table here. So this will be the iteration. Next, that will be the xi. Then it will be xi plus 1. Then we'll be comparing it with absolute value of epsilon t. So iteration. In Newton-Raphson method, particularly, we start from 0th iteration. Although it's up to you, but to make compliance with our derived formula or using formula the book we are following, the Newton-Raphson method should be started from 0th iteration. That will be better for us. This is xi, and this will be xi plus 1, which will be used as xi in the next iteration, and finally the epsilon t in percentage will be calculating here. As we know the true root, this is the true root, we are assuming using calculator, so this one will be getting here. So how to obtain the true root, that might be a question. So I think you know how to calculate the true root using your calculator. What you can do, that this is the initial gaze, so you can write up the function in calculator as say for example you will be writing this e to the power minus x equals to 0. This will be your function in the calculator, the scientific calculator you are using. So you'll be writing this epsilon, this x, using the alpha mode. After pressing you can write x, alpha mode you can write this x, and using alpha mode you can write this equal sign as well. Using alpha mode, pressing alpha after that calc will give you this equals mode, then equals to 0. After you created this equation in the calculator, then you press shift plus calc. Then it will ask solve for x, that means x equals to what? So then you put the value x not equals to 0, that is 0. Give you input as 0 and press equal, then it will give you this true root. So try in your scientific calculator, it will give you the root as I have shown. So that's how we will be calculating this one and comparing now this with the approximate values. So 0th iteration, it says that you should start from 0, and that's why the initial gaze will be 0. So if you put the value 0 in this equation, 0, it will become 0, it will become 0, it will become 1, and it will become minus 1, so minus 2, 1 by minus 2, and there is a minus over there, so it will become half, that is 0.5. So using calculator as well you can calculate this one, this will become 0.5, and obviously you can calculate the true error here. True error, we can calculate point. In this case, as our initial gaze is 0, so it will become 100% of true error. Anyway, for the next iteration, xi plus 1 will be moved to xi, and using this one, remember one thing, this one we have calculated for this xi. Don't be confused about this one. So therefore, now we'll be calculating true error when our gaze is 0.5. So that means the true root minus 0.5 divided true root multiplied by 100% is this one. It will be this one. So if you calculate, this is the true root. Using this one, the value we'll be obtaining is 11.8%. and this is not less than the stopping criteria, 10 to the power minus 8. So it is greater than 10 to the power minus 8%. So we need to go further. And what will be the value of xi plus 1? If you put the value of 0.5 over there, 0.5, 0.5, 0.5, then what will be the value of xi plus 1? The xi plus 1 will be, in this case, will be 0.566, as much digit as you can, 0032, just because very higher accuracy required. So this will be going to the next state, next iteration. This will be the value 0.566 311 0032, and let's calculate the error in this case. So the true root we know, and this is the current approximation divided by true root will give you an answer. You can also compare 0.56631, so the true root is 56714, so it will be very close, but not as close as we are expecting. So it will give you 0.147% of accuracy. Think about it. Very, very converging in Newton-Raphson method. So however, what will be the value of xi plus 1 in this case, using this one? So this one will be xi in this equation. So that's how you will be obtaining the value. This will be 0.567 1431 65. 567143165. Okay, so this value will be going to the next iteration to check whether it converges or not and whether it satisfies the criteria. Using this value, and this is more close to the original true root, if you can see here. Okay, using this value, you compare it with the true value 567143165. You see the true value 56714329004. See, up to 5 to from 5 up to 3, it is similar. So very close to the solution. So let's calculate the true epsilon t percent relative true error, and it will be 0.0002211, but still then it is greater than 10 to the power minus 8%, and that's why we need to go for another step. And let's calculate xi plus 1 from this equation, which will give you, using this xi, it will give you the value of 0.56714329004, which is exactly equals to the true root here. So no problem about this, and this will, whenever I will be picking up this one here, 32904, I can just write it will obviously give you less value than 10 to the power minus 8%. How I can say that? Just because whenever you are using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 digits are equal. So that's why you can say it will obviously less than 10 to the power minus 8%, or at least your calculator cannot go beyond that. So you can say it is 0% in your case. But remember one thing, that's why I was asking you to take as much digits as possible. If you don't take as much digits as possible, you may get wrong values in these points. You might obtain, I have seen in your class test as well, as you have rounded this value in 2 or 3 digits. I have said from the very first class that in numerical method you'll have to take as much values as you can using your calculator. As you have rounded the values, you have obtained values 0% error in many cases. But it is not the case. That will not signify the epsilon t, the concept or philosophy. You have to take as much value as possible. So in this case, as we cannot go beyond that, it will obviously become less than 10 to the power minus 8%, and eventually it will be 0% obviously in your case according to your calculator. And in your exam, I will try to give you the exam questions or mathematical problems in such a manner so that obviously it will be compliant with your calculator what you are using. And in case where this will become at the last limit, then you will be stopping there in cases if such case arises as we have seen here. So whatever, even in this case, we can say this will be less than 10 to the power minus 8%. This is the last step where this will be finalized, whatever it is. So that's how you have to approach. This is the answer. Our answer is also this one, what we have obtained from the true root using calculator. And we can say indirectly our calculator, the calculator is also another computer, as you know. So that's why our calculator, what it has given this one using a solve for zero initial guess, we can say it is also using the Newton-Raphson method. It might have used Newton-Raphson method within the calculator for calculating this true root. Well, anyway, now I'll be finishing our today's class. Before I explain this thing. So this is the next true error, next steps true error. This is the initial this current true error. This is the true root. Using this one you can predict the next true error from the current true error. Okay, so before that I will have to rearrange it using our these values. So f double prime fxr, that is e to the power minus x. If we put the value xr, that is true root, if it is put, we put this here, we'll obtain a value also 2f prime xr, that is in this point if we put the value of original root here, you'll get again the value. Then we'll be getting a value of this one. So I can write it like eti plus 1 will be equals to, I can write it like 0.56714 and divided by 2 multiplied by minus 1.56714329 using the true root values in these two functions. Okay, so we can write it as 0.18095 ETI square. So using this one I can predict the next error using one true error. So for example, if we start from the very starting point, that in this case we have assumed the value as 0, the true error was 100%. So as the true error was 100% relative error, but if we take the original true error for 0th iteration, if we say it is the percent relative true error, but the original true error is the this true root minus the approximation, that is the value of original root, the 56714,329. The true root value will be the true error in the first case, just because true error ET is nothing but true value minus approximation. So approximation, as it is 0, so it will be equals to the true value in the first case. So this one. So if you put the value here, in this case, you will get ET1 equals to, approximately equals to, you will be getting the value as 0.0582. Whereas if you calculate it using this 0.5 and the true root minus 0.5, if you take the value, the original value, this is formula, this is original, ET1 is equals to true root minus 0.5. That will be equals to, that will be equals to close to the original solution. If you calculate the true value, true error will be getting 0.0, everything just except 0.5 will be deducted, as we are subtracting 0.5. So 0.5 will be subtracted and all other things will be similar, 4329. So this is the true value and this is the approximation. So this is the fact what it says. So again, if you want to know the approximate value of second iteration using this formula, then you will have to put their ET1 square value here with multiplied with 0.18095. that will give you an approximate value of ET2. So ET2, if we calculate, and obviously this value, this ET1 value will be putting the original value, not this approximated one. So this original value, if you put here and multiply it with this one, you will be getting an approximate value which will be equals to 0.0008158. And if you calculate the original true error in the second step, that is using while we have used this value, and the true root was 0.56714,329 minus 0.5663110032. Our root was our error was 0.00083286. In our case, this is the true error. So this is the approximation. That's why this is close to this one. So that's why this formula was mentioned in your slide. This formula, that we can predict from any true error at any one step and predict the error of the next step using this formula. That's why it was mentioned. So if you are asked to vindicate, then you will be vindicating or approximating. And other than that, if you are asked to just satisfy the criteria, then you will have to determine this answer, and that will be your answer in the answer script. So that was all for us today. So I will not move further. Today I will be finishing our class lecture. We have 2 more weeks to complete this theoretical portion, and hopefully we'll be able to complete it successfully. Thank you, everyone.